Preliminary Chapter 2. What is a limit? It is possible, though difficult to understand, calculus without a firm grasp on the meaning of a limit. A derivative, the fundamental concept of differential calculus, is a limit. An integral, the fundamental concept of integral calculus, is a limit. To explain what is meant by limit, we will be concerned in this chapter only with limit of discrete function because limits are easier to understand in discrete terms. When you read Calculus Made Easy, you will learn how the limit concept applies to what are called function of a continuous variable because their variable have real number value that vary continuously. Function of discrete variable have variable whose value jump from one value to another. There are also functions of complex variable in which value are complex number based on the imaginary square root of -1. Complex variables are outside the scope of Thompson book. A sequence is a set of a number in some order. The number don't have to be different and they need not to be integer. Consider sequence 1, 2, 3, 4. This is just a positive integer. It is an infinite sequence because it continues without stopping. If it stopped, it would be finite sequence. If the terms of a finite sequence are added to obtain finite sum, it is called a series. If a series is infinite, the sum to any specified terms is called partial sum. If the partial sum of an infinite series get closer and closer to a number k so that they continue the series, you can make the sum as close to k as you please. The k is called the limit of the partial sum or the limit of the infinite series. The terms are said to be convergent k if there is no convergence. The series is said to be divergent. The limit of an infinite series is sometimes called its sum at infinity. But of course this is not a sum in the usual arithmetical sense when the number of terms is finite. You can't obtain the sum of an infinite series by adding because the number of terms to be added is infinite. When we speak of the sum of an infinite series, this is just a short way of naming its limit. An infinite series can converge on its limit in three different ways. The partial sum get ever closer to limit without actually reaching it, but they never go beyond the limit. The partial sum reach the limit. Partial sum go beyond the limit before they converge. Let's look at example of type 1 and 3. 15th century BC, Greek philosopher Zeno of Elea invented several famous paradoxes intended to show that there is something extremely mysterious about motion. One of them, imagine a runner going from A to B. He first run half the distance, then half the remaining distance, then again half the remaining distance, and so on. The distance he runs gets smaller and smaller in the half series. 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 and so on 1 upon 2 raised to n. Distance from B approach 0 as their limit while the distance from A from series that converge on 1. The runner of course model a point moving along a line from A to B. Does the runner ever reach the goal? It depends. Assume that after each step in the series, the runner pauses to rest for a second. We can model this with a pawn representing a point that you push across the table from one edge to the edge of the opposite. First you push the pawn half the distance, then pause for a second. You push it half the remaining distance and again pause for a second. If this procedure continues, the point will get closer and closer to the limit, but will never reach it. There is an old joke based on it. A mathematics professor places a male student at one side of an empty room and a gorgeous female student at the opposite wall. When command the boy walk half the distance towards the girl. Wait a second, then goes half the rest of the way, and so on, always pausing a second before he cuts the remaining distance in half. The girl say, haha, you will never reach me. The boy replied, true, but I can get close enough for all practical purpose. Suppose now that instead of waiting a second after each pawn, push the pawn in mode at a steady rate. Assume that the constant speed is such that pawn goes half the distance in 1 second, half the remaining distance in half a second, and so on. No pause. A discrete process has been transformed into a continuous one. In 2 seconds, the pawn has reached the table far edge. Zenorana, if he goes at a steady rate, will reach the goal in a finite period of time. The halving series model in this fashion converge exactly on the limit. Zenorana leads to a variety of amusing paradoxes involving what are called infinity machines. A simple A simple example is a lamp that is turned off at the end of a 1 minute, then turned on at the end of a half a minute, of after a quarter minute, and so on. In an infinite series of ons and off, the time series converges on 2 minutes. At the end of 2 minutes, is the lamp on or off? This, of course, is a thought experiment. It can't be performed with an actual lamp, but can it be answered in the abstract? No, because there is no large operation in an infinite series of on and off. It is like asking if the last digit of pi is odd or even star. An easy way to see what the limit of 1 by 2 plus 1 by 4 plus 1 by 8 plus is 1 is to mark off the fractional length along a number line as Thompson does in his figure 46. A similar look-see proof that series converge on 1 is shown by the dissected section unit square in figure 6. The 1 by 8 plus 1 by 16 plus so on is equal to 1. A two-dimensional look-see proof that 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 60 and so on equal to 1. On infinity machines, see Aleph and Super Task, Chapter 4 in My Real Life and Other Mathematical Amusement, W.H. Freeman, 1983, and the reference cited in that chapter bibliography. Partial sum of the series are generated by the discrete function 1 is 1 upon 2 raised to n, where n takes the integral value 1, 2, 3, 4, 5. We turn now to an infinite series that goes past its limits before finally converging. An example is provided by changing every other sign in the halving series to a minus sign. 1 by 2 minus 1 by 4 plus 1 by 8 minus 1 by 16 plus so on. The partial sum of these alternating series are alternately above and below the limit of 1 by 3. The difference from 1 by 3 can be made as small as you please, but every other partial sum is larger than the limit. As an infinite series approaches but never reaches its limit, the difference between a partial sum and the limit get closer and closer to 0. Indeed, they get so close that you can assume they are zero, and therefore, as Thompson liked to say, they can be thrown away. An early book on calculus terms said to become infinitely close to zero were called infinitesimals. Clearly, there is something spooky about number living in a neverland that is infinitely close to zero, yet somehow not zero. In the halving series, for example, the fractions approaching zero never become infinitesimals because they always remain a finite portion of one. Infinitesimals are infinitely smaller part of one. They are smaller than any finite fraction you can name, yet never zero. Are they legitimate mathematical entities, or should they be banished from mathematics? The most outspoken opponent of infinitesimal was the 18th century British philosopher Bishop George Berkeley, who attacked them in a 1734 book titled The Analyst, or discourse addressed to an infidel mathematician. The infidel was the astronomer Edmund Halley, for whom Halley's comet is named, and the man who persuaded Newton to publish his famous Principia. Here are some of Bishop Berkeley's complaints about infinitesimal. Fluxion was Newton's term for a derivative. And what are these fluxion? The velocity of evanescent increments. And what are the same evanescent increments? They are neither finite quantity nor quantity infinitely small, nor yet nothing. May we not call them ghosts of departed quantities? And of the aforesaid fluxion, there be other fluxion, which fluxion are called second fluxion, and the fluxion of the second fluxion are called third fluxion, and so on, fourth, sixth, fourth, fifth, sixth, etc. ad infinitum. Now, as our sense is trained and puzzled with the perception of object extremely minute, even so imagination, which faculty derives from sense, is very much strained and puzzled to frame clear idea of less particle of time, other least incremented generated therein, and much more to comprehend the moment. All those increment of flowing quantity in status nascently in their first origin or beginning to exist before they become finite particle, and it seems still more difficult to conceive the abstract velocity of such nascent imperfect entities, but the velocity of the velocities, the second, third, fourth, and fifth velocity, etc., exceed, if I mistake not, all human understanding. The further the mind analyses it, the persuade this fugitive idea, the more it is lost and bewildered. The object at first fleeting and minute sound vanishing out of sight. Certainly, in any sense, the second or third fluxion seem an obscure mystery. The incipient celerity of an incipient celerity, the nascent augment of a nascent augment, that is, of a thing which hath no magnitude, that it is it in what light you please. The clear conception of it will, if I mistake, not to be found impossible. Whether it be so or no, I appeal to the trial of every thinking reader. And if the second fluxion be inconceivable, what are we to think of third, fourth, sixth fluxion, and so on without end? He who can digest a second or third fluxion, a second or third flux difference, need not, methink, be squeamish about any point in divinity. Johann Bernoulli, a Swiss mathematician who did pioneering work in developing calculus, expressed the paradox of infinitesimal crisply. They are so tiny, he said, if a quantity is increased or decreased by an infinitesimal, then the quantity is neither increased nor decreased. For 2 centuries, most mathematicians agreed with Berkeley and refused to use the term. You wouldn't find it in calculus made easy, Bernard. Bernard Russell in Principle of Mathematics 1903, chapter 13 and 40 has a rigorous attack on infinitesimal. He called them mathematically useless, unnecessary, erroneous, and self-contradictory. As late as 1941, the noted mathematician Richard Gordon wrote, "Infinitely small quantity are now definitely and dishonorably discarded." Like Russell and others, he believed that calculus should replace infinitesimal by the concept of limits. Charles Peirce, 1839 to 1914, America's great mathematician, philosopher, and friend of William James, strongly disagreed. He was almost alone in his day in sliding with Leibniz, who believed the infinitesimal were as real and as legitimate as imaginary number. Here are some typical remarks by Peirce that I found by checking infinitesimal in the index of the volume and make a PSA collector paper and his new element of mathematics. Infinitesimal may exist and be highly important for philosophy as I believe they are. The doctrine of infinitesimal is far simpler than the doctrine of limit. Is it consistent freely to admit of imaginaries while rejecting infinitesimal as inconceivable? Infinitesimal in the strict and literal sense are perfect, intelligible, contrary to the teaching of the great body of modern textbooks on the calculus. There is nothing contradictory about the idea of such quantities. As American as a mathematician, I prefer the method of infinitesimal to that of limit as far easier and less infested with snares. Pierce Come would have been delighted that he lived to see the work of Abraham Robinson of Yale University. In 1968, to the vast surprise of mathematicians everywhere, Robinson found a way to reintroduce Leibniz infinitesimal as legitimate, precisely defined mathematical entity. His way of using them in calculus is known as non-standard analysis. Analysis is a term applied to calculus and all higher mathematics that use calculus. Non-standard analysis have produced simpler solutions than standard analysis to many calculus problems. And of course, it is closer to an intuitive way of interpreting infinite converging series. Robinson's achievement is too difficult to go into here, but you will find a good introduction to it in Non-Standard Analysis by Martin Davis and Vivian Harsh in Scientific American, June 1972. Mathematician and science fiction writer Rudy Rucker in his book Infinity and the Mind, 1982, vigorously defend infinitesimals. So great is the average person's fear of infinity that to this day calculus all over the world is being taught as study of limit process instead of what is really is infinitesimal analysis. As someone who has spent a good portion of his adult life teaching calculus courses for a living, I can tell you how weary one get of trying to explain the complex and fiddling theory of limit to wave after wave of uncomprehending freshmen, but there is a hope for a brighter future. Robinson's investigation of the hyperreal numbers have put infinitesimal on a logical, unimpeachable basis, and here their calculus texts based on infinitesimal have appeared. Which is preferable, to talk about quantities so infinitely small that you can, as Thompson say, throw them away, or to talk of fairly approaching a limit? Debate over the infinitesimal versus the limit language goes nowhere because they are two ways of saying the same thing. It's like choosing between calling a triangle a polygon with three sides or a polygon with three angles. Calculation in differentiating or integrating are exactly the same, regardless of your preference for how to describe what you are doing. Now, the infinitesimal have become respectable again, thanks to non-standard analysis. You needn't hesitate if you like to use the term. You might suppose that if the term of an infinite series gets smaller and smaller, the series must converge. This is far from true. The most famous example is 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5 plus so on, known as harmonic series. It has countless applications in physics as well as in mathematics, although its fractions get progressively smaller, converging on zero. Its partial sum grow without limit. The growth is infuriatingly slow. After 100 terms, the partial sum is only a bit higher than 5. To reach a sum of 100 require more than 10 raised to 43 terms. If we eliminate all terms in the harmonic series that have even denominator, will it converge? Amazingly, it will not. Thought its rate of growth is much slower. If we eliminate from the series all terms whose denominator contains specific digit one or more time, the series will then converge. The following table gives two decimal places the limit for each omitted digit. Omitted digit sub 1. Omitted digit 1 is sum is 16.18. Omitted digit 2 is sum is 19.26. Omitted digit 3 is sum is 20.57. Omitted digit 4 is 21.33. Omitted digit 5 is 21.83. Omitted digit 6 is 22.21. Omitted digit 7 is 22.49. Omitted digit 8 is 22.73. Omitted digit 9 22.92. Omitted digit 0 is 23.10. Limit of infinite series can be expressed by unending decimal fraction. For example, 0.33333 so on is the limit of the series 3 upon 10 plus 3 upon 100 plus 3 upon thousands plus so on equal to 1 by 3. Incidentally, there is a ridiculously easy way to determine the integral limit of any repeating decimal. The trick is to divide the repeated sequence of digits by a number consisting of the same number of 9 as their digit in the repeated. Thus 0.333 so on reduces to 3 by 9, 1 by 3. If the repeating decimal is 0.123123123 so on, the limit is 123 upon 999, which reduced to 41 upon 333. Irrational numbers such as irrational roots and transition numbers such as pi and e are limits of many infinite series. Pi, for example, is the limit of such highly patterned series as 4 by 1 minus 4 by 3 plus 4 by 5 minus 4 by 7 plus 4 by 9 minus so on. The number A you will encounter it in Thompson's chapter 14 is the limit of 1 plus 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial plus. Although Archimedes did not know calculus, he anticipated integration by calculating pi as the limit of perimeter of regular polygon as the numbers of slight increase. In the language of infinitesimal, circle can be viewed as perimeters consisting of an infinity of straight line segments, each of infinitesimal length. Many ingenious techniques have been found for determining if an infinite series converge or diverge, as well as ways sometimes not easy of finding the limit. The term of a series decreases in a geometric progression. Each term is the same fraction of the preceding one. Finding the limit is easy. Here is how it works on halving series. 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 so on. Let x, the entire series, multiply each side of the equation by 2. 2x equal to 2 plus 2 by 2 plus 2 by 4 plus 2 by 8 plus 2 by 16 plus so on. Reduce the term. 2x equal to 2 plus 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus so on. Note that the series beyond 2 is the same as original halving series, which we took as x. This enables us to substitute x for the sequence and write 2x equal to 2 plus x. Rearranging the series to 2x minus x equal to 2 gives x the limit of the series, a value of 2. The same trick will show that 1 by 2 is the limit of 1 by 3 plus 1 by 9 plus 1 by 27 plus 1 by 81 plus and so on. It works on any series in which term decrease in geometric progression. Bouncing ball problems are common in the literature on limits. They assume that an ideally elastic ball is dropped a specified distance to a halved flow. After each bounce, it rises a constant fraction of the previous height. Here is a typical example. The ball is dropped from a height of 4 feet. Each bounce takes it to 3 by 4, the previous height. In practice, of course, a rubber ball bounces only a finite number of times, but idealized ball bounces an infinite number of times. The rise approaches 0 as a limit, but because the time of each bounce also approaches a limit of 0, the ball, like Zeno runners, finally reaches the limit. After an infinity of bounds, it comes to rest. After a finite period of time, when ball ceases to bounce, how far has it traveled? We can solve this problem by using the same tricks used on the halving series. Ignoring for a moment the initial drop of 4 feet, the ball will rise 3 feet, then fall 3 feet for a total of 6 feet. After that, each bounce rise plus fall is a 3/4 the previous bounce, letting x be the total distance the ball travel after the first drop of 4 feet. We write the equation x is equal to 6 plus 18 upon 454 upon 61 plus 162 upon 64 plus 486 upon 256 plus and so on. Reducing the fraction x equal to 6 plus 9 by 2 plus 27 by 8 plus 81 by 32 plus 243 by 128 plus. Because each of term is 4 by 3 is following term, we multiply each side by 4 by 3 to get 4x upon 3 equal to 8 plus 6 plus 9 by 2 plus 27 by 8 plus 81 by 32 plus. Observe that after 8 the sequence is the same as x, so we can substitute x for it. 4x by 3 equal to 8 plus x, 4x equal to 24 plus 3x, x is equal to 24. This is the distance the ball bounced after the initial drop of 4 feet. The total distance traveled by the balls is 24 plus 4 is equal to 28 feet. Sam Lloyd, America's great puzzle maker, in his Cyclopedia of Puzzles, page 23, and his British counterpart Henry Ernest Dewdney in Puzzle and Curious Problem 2023, each give the following ball bounce problem. A ball is dropped 179 feet from the Tower of Pisa. Each bounce is 1/10 the height of the previous bounce. How far does the ball travel after an infinity of bounce before it finally comes to rest? See figure 7. We can solve this by trick used before, but because each fraction is 1/10 the previous one, we can find answer by an even faster method. After the initial drop of 179 feet, the height of first bounce is 17.9. Succeeding bounce have height of 1.79, 0.179, 0.0179 and so on, with the decimal point moving one position left after each bounce. Adding this height gives a total of 19.8888. We now double this distance to obtain the up plus down distance for each bounce to get 39.777. Finally, we add the initial drop of 179 feet. So to obtain the total distance, the ball travels 218.7777 or exactly 218 and 7 by 9 feet. Converging series that do not decreases by a geometric progression often can be solved by other clever methods. Here is an interesting example. X equal to 1 plus 3 by 2 plus 2 5 by 4 plus 7 by 8 plus 9 by 16 plus 11 by 32 plus so on. Note that the numerals are odd number in sequence and denominator are double series. Here is simply way to find the limit. First divide each term by 1 by 2. X divided by 2 is equal to 1 by 2 plus 3 by 4 plus 5 by 8 plus 7 by 16 plus so on. Subtract this sequence from the original sequence. S equal to 1 plus 3 by 2 plus 5 by 4 plus 7 by 8 plus 9 by 16 plus and so on. X by 2 equal to 1 by 2 plus 3 by 4 plus 5 by 8 plus 7 by 16 plus so on. X by 2 equal to 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus 1. Observe that after the 1 inside the bracket, the sequence that follow is our old friend, the having series, which we know converge on 1. Adding 2 to the initial 1 give the series a limit of 3. Since 3 is half of x, x must be 6, the limit of the original series. Thompson does not much time on series and their limits. I have done so in this chapter for two reasons. They are the best way to become comfortable with the limit concept, and modern calculus textbooks now usually include chapter and infinite series and their usefulness in many aspects of calculus. What is derivative? And the preliminary chapter 3. Preliminary Chapter 3. What is derivative? In Chapter 3, Thompson's make crystal clear what a derivative is and how to calculate it. However, it seemed to me useful to make a few introductory remarks about derivative that may make Thompson's chapter even easier to understand. Let's start with Zeno's runner. Assume that he used 10 meter per second on path from 0 to 100 meter. The independent variable is time, represented by the x-axis of the Cartesian graph. The dependent variable y is the runner distance from his starting spot. It is represented on the y-axis. Because the function is linear, the runner motion graph has an upward tilted straight line from 0. The graph's origin to the point that is 10 seconds on the time axis and 100 meter on the distance axis. Figure 8. If by distance we mean distance from the goal, the line on the graph tilts the other way. Figure 9. Given any point in time, how fast is the runner moving? Because we are dealing with a simple linear function, we don't need calculus to tell us that at every instant he is going 10 meters per second. The function's equation is y equal to 10x. Note that the slope of the line on the graph as measured by the height in meter at any point divided by the elapsed time in second at any point is 10. At each instant, the runner has gone in meter 10 times the elapsed number of seconds he instantaneous speed throughout the run clear is 10 meters per second. Consider any movement of the time along the x-axis, then go vertically, go up the graph to the distance traveled in meter. You will find that distance is always 10 times the elapsed time, as you will learn when you read calculus made easy. The derivative of a function is simply another function that describes function is simply another function that describes the rate at which a dependent variable changes with respect to the rate at which independent variable changes. In this case, the runner speed never changes, so the derivative of y equal to 10x is simply the number 10. It tells you two things. One, that at any time the runner speed in 10 meters per second, and two, that at any point on the line that graph this function the slope of the line is 10. This generalizes to all linear functions in which the variable y changes with respect to variable x at a constant rate. If a function is y equal to ax, its derivative is simply the constant a. As I said, you don't need calculus to tell you all this, but it is good to know that calculating derivative gives the correct result even when functions are linear. An even simpler case of a derivative too obvious to require any thoughts, let alone demanding calculus, is the case of a runner who stands perfectly still. Let's say he stopped running after going 10 meters. The function is y equal to 10. The graph becomes horizontal straight line as shown in figure 10. Its slope is 0, which is the same as saying that the rate at which the runner distance from the start change relative to change of time is 0. The function derivative is 0 even in this extreme case. It is comforting to know the calculus still applies. In general, the derivative of any constant is 0. Calculus ceases to be trivial when functions are nonlinear. Consider the simple nonlinear function is y equal to x raised to square, which Thomson uses to open his chapter on derivative. Let's see how it applies to the growth of a square. The simplest geometrical interpretation of this function. Imagine a monster living on a flat land, a plane of 2 dimensions. It is born a square of a side 1 and area 1, then grow at a steady rate. We wish to know at any instant of time how fast its area grows with respect to the growth of its side. The monster's area, of course, is the square of its side. So the function we have to consider is y equal to x raised to square, where y is the area, x the side. It graphs as the parabola shown in figure 1 of the first preliminary chapter. As you will learn from Thomson, the function derivative is 2x. What does this tell us? It tells us that at any point moment the monster's area is growing at a rate that is 2x times as fast as its side is lengthening. For example, let's say the monster's side is growing at a rate of 3 units per second. Starting with a side of 1 unit at the end of 10 seconds, its side will have reached 31 units. The value of x at this point is 31. The derivative said that when the monster's side is 31, its area is increasing with respect to its side at a rate of 2x, or 2 multiplied by 31 equal to 62 units. When the square reaches 100 on its side, its area will be increasing with respect to its side by 2 multiplied by 100 equal to 200 units. This figure expresses the rate of the square growth with respect to its side. For the square growth rate with respect to time, we have to multiply this value by 3. Thus, when the square has a side of 31 after 10 seconds, it is growing at a rate of 3 multiplied by 2 multiplied by 31 is equal to 186 square unit per second. When the side is 100, its growth rate per second is 3 multiplied by 2 multiplied by 100 is equal to 600. Suppose the monster is a cube of edge x with increase at a steady rate of 2 units per second. The cube's volume y is x cubed. The derivative of the function y equal to x cubed is 3x squared. This tells you that cube's volumes in cubical unit growth 3x squared times as fast as its edge grows. Thus, when the cube side reaches say 10, the value of x is volume is growing 3 multiplied by 10 raised to square 300 equal to 300 square inches as far as its side. Its growth rate per second is 2 multiplied by 2 multiplied by 10 raised to square 600. Although Thomson avoided defining a derivative as the limit of a sequence of ratio, this clearly is the case. Suppose, for instance, that our growing square has side that increase at 1 unit per second. We can tabulate the area growth at time slightly larger than 2 seconds as follows. Time side area 2, 3, time 2 have slide 3, area is 9. Time 2.1 has slide 3.1, area is 9.61. Time 2.0.01, area 9.060. Time 2.00, its is 0.001, area 0.06. The average rate of growth from time 2 to time 2.1 is 9.61 minus 9 upon 2.1 minus 2 equal to 6.1, and from time 2 to time 2.01, 9.0601 minus 9 divided by 2.01 minus 2 equal to 6.01, and from time 2 to time 2.001, 9.006001 minus 9 divided by 2.001 minus 2 is equal to 6.001. The averages obvious approaches a limit of 6. Thus, the derivative of the area with respect to time is the limit of an infinite sequence of ratios that converge on 6. A simpler derivative is the rate at which a function-dependent variable grows with respect to growth rate of the independent variable. In geometrical terms, it determines the exact slope of the tangent to a function curve at any specified point along the curve. This equivalence of the algebraic geometrical definition of derivative is one of the most beautiful aspects of calculus. I hope this and the previous two preliminary chapters will help prepare you for understanding calculus made easy. Calculus made easy. What one fool can do, another can. Ancient Seaman Proverbs. Publisher note on the third editions. Publisher's note on the third edition. Only once in its long and useful life in 1919 has this book been enlarged and revised, but in 26 years much progress can be made, and the methods of 1919 are not likely to be the same as those of 1945. If therefore any book is to maintain its usefulness, it is essential that it should be overhauled occasionally so that it may be brought up to date where possible to keep pace with the forward march of scientific development. For the new edition, the book has been reset and the diagram modernized. Mr. F. G. W. Brown has been good enough to revise the whole of the book, but he has taken great care not to interfere with the original plan. Thus, teachers and students will still recognize this well-known guide to the intricacy of the calculus. While the change made are not of major kind, yet their significance may not be inconsiderable. There seems no reason now, even if one ever existed, for excluding from the scope of the text those intensely practical functions known as hyperbolic, sine, cosine, and tangent, whose application to method of integration are so potent and manifold. This have accordingly been introduced and applied with the result that some of the long cumbersome method of integrating have been displaced just as a ray of sunshine dispels on obstructing cloud. The introduction too of the very practical integration e raised to pt sine kt dt and e raised to pt cos kt multiplied by dt has eliminated some of the more ancient method of finding solution. Chapter 21 by their application, shorter and more intelligible, one have grown up naturally. Instead, in the treatment of substitution, the whole text has been tidied up in order to render it methodically consistent. A few examples have also been added where space per meter, while the whole of the exercise and the answer have been carefully revised, checked, and corrected. Duplicated problems have thus been removed, and many hints provided in the answer adapted to the newer and more modern method introduced. It must, however, be emphatically stated that the plan of the original author remained unchanged, even in its more modern form. The book still remained a monument to the skill and the courage of the late Professor Sylvanus P. Thompson. All that the present reviser has attempted is to revitalize the usefulness of the book by adapting its distinctive utilitarian bias more closely in relation to present-day requirement. Prologue. Considering how many fools can calculate, it is surprising that it should be thought either difficult or a tedious task for any other fool to learn how to master the same tricks. Some calculus tricks are quite easy, some are enormously difficult. The fools who write the textbook of advanced mathematics, and they are mostly clever fools, seldom take trouble to show you how easy the easy calculations are. On the contrary, they seem to desire to impress you with a tremendous cleverness by going about it in the most difficult way. Being myself a remarkable stupid fellow, I have had to unteach myself the difficulties, and now beg to present to my fellow fools the parts that are not hard. Master this thoroughly, and the rest will follow. What one fool can do, another can. Common Greek letter used as symbol. Capital A, small alpha. Capital B, beta. Capital L, gamma. Capital D, delta. Capital E, epsilon. Capital H, eta. Capital O, theta. Capital K, kappa. Capital V, lambda. Capital M, mu. Capital Z. Capital P, pi. Capital P, rho. Sigma. Phi, omega. Chapter 1. To deliver you from the preliminary terror. The preliminary terror which chokes off most high school students from even attempting to learn how to calculate can be abolished once for all by simply stating what is the meaning in common sense terms of the two principal symbols that are used in calculating. These dreadful symbols are 1. D, which merely means a little bit of. Thus dx means a little bit of x. Du means little bit of u. Ordinary mathematicians think it more polite to say an element of instead a little bit of, just as you please, but you will find that this little bit or element may be considered to be infinitely small. Number 2, integration, which is merely a long s and may be called, if you like, the sum of. Thus, integration dx means the sum of all the little bit of x, or integration dt means the sum of all the little bit of t. Ordinary mathematicians call the symbol the integral of. Now any fool can see that if x is considered as made up of a lot of little bit, each of which is called dx, if you add them all up together, you get the sum of all dx's, which is the same thing as the whole of x. The word integral simply means the whole. If you think of duration of time for 1 hour, you may, if you like, think of it as cut up to 3600 little bit called seconds. The whole of the 3600 little bit added up together make 1 hour. Thus, you see an expression that begin with this terrifying symbol. You will henceforth know that it is put there merely to give you instruction that you are now to perform the operation, if you can, of totaling up all the little bits that are indicated by the symbol that follow. That's all.